Okay, we have a mean value theorem problem here. We are to determine if the mean value theorem applies to the function below, that's this function right here, over the interval given, here we go, and if it does, we need to find the points, so we're after some ordered pairs here, on the graph that are guaranteed to exist by the theorem. And if it doesn't, we need to explain why. So the first step, of course, is to remind ourselves what the mean value theorem says. Recall, the mean value theorem tells us if we have a function which is continuous over a closed interval, endpoints are included, and if that same function is differentiable over the open interval with the same endpoints, then there has to exist at least one value c, now this is an x value, an input to our function, in this open interval from a to b, the same one we used here, where the derivative at that x value, at c, equals some fairly special expression here, this f of b minus f of a over b minus a. Now, why is this a special expression? Well, if we look at the graph of such a function, and notice here is our interval from a to b, then this expression here represents a slope of a special secant line to our graph, namely the secant that intersects the graph of f of x at the endpoints of our interval, at a, and over here at b. Now, how do I know that the slope of this secant line is this? Well, recall how you find slope. Slope is rise over run, right? Well, what is the rise of this red line between x equals a and x equals b? Well, that would be the length of this blue segment, or the length here between f of b and f of a, or the difference between those two things. There it is, f of b minus f of a. And how long is the run? Well, the run is the length of this blue segment, or the length of this segment here between a and b, or consequently the difference between b and a. Notice that's here, b minus a. So what the mean value theorem is guaranteeing is that there is some c in between these 2 points. In this drawing, it might be right here, where if we look at the derivative, or the slope of the tangent line to the curve, the slope of that tangent line is going to agree with the slope of this secant line. In other words, these two things are parallel. But getting back to our problem, we need to determine if the mean value theorem applies to the function below. How do I tell that? Well, I need to look at these conditions. This right here is the hypothesis of this theorem. If these conditions hold, then you can conclude something by the mean value theorem. So I need to know that f of x is continuous over that closed interval, and I need to know that f of x is differentiable over that open interval. So we check the conditions needed first. The first condition, of course, is the one dealing with continuity. Is f of x continuous on the interval they gave us? And more importantly, why? How do I know f of x is continuous? I need to come up with some argument for how I know f of x is continuous. Well, look at what f of x is. This is a nice, pretty polynomial function. We know something about continuity in polynomials. All polynomials are continuous everywhere. So certainly, this function has to be continuous in this interval. It's continuous on all reals. Okay? So the answer to our first question is simply yes, but we need to justify that. We need to write something equivalent to all of this. Okay? F of x equals this guy right here. It's a polynomial function. We know polynomials are continuous everywhere, so certainly it's continuous on the interval given. Okay? So we've passed the first condition. That holds. What about the second condition? Do I know if it is differentiable on the open interval with the same endpoints? Okay? And here again, it's just as important to give a good justification for this. You can't just answer yes or no. We need to know why. Well, I suppose in trying to answer this question, you could go back to the limit definition of the derivative, but that's a lot of work, right? Especially given that this is a cubic. Far easier if we have access to the little tricks that let us find derivatives to see if we can find it here. If we can find it, the derivative certainly exists, and if it exists, it's differentiable. Now, don't we know, because f of x is this polynomial, that the derivative must be 3x squared minus 6x plus 2, just applying the power rule to each term here? Is there any x value for which this is a problem? Is there any x value that I won't be able to evaluate f prime of x at? Well, no. This is a polynomial too. And polynomials have a domain of all reals. I can plug anything in to a polynomial function. So it won't have any problems over the entire reals, so it's certainly not going to have any problems over the interval from 0 to 2. So just like above, we need to write something to that effect. Maybe something like this. Yes, we know it's differentiable. Here's the derivative. Notice it's a polynomial, and thus it's defined for all reals, so certainly f prime of x is defined on 0, 2, which makes it differentiable. Great. We have continuity over the appropriate closed interval. We have differentiability over the appropriate open interval. We have met both conditions of the mean value theorem, and as such, we can conclude the mean value theorem does apply. Okay, so we have answered the first part of this problem. But we must do more. We need to find the points on the graph that are guaranteed to exist by the theorem. The mean value theorem guarantees the existence of some input c that will result in a point on the graph where the derivative at c matches that slope of the secant line we talked about earlier. Let's scroll things up a little bit so we have some room to work. So again, the mean value theorem is going to force the existence of some c in this open interval from 0 to 2 where the derivative of c equals this slope of a secant line, namely f of 2 minus f of 0, over that run we talked about earlier of 2 minus 0. Now, how do we find this value of c? Well, notice the mean value theorem doesn't tell us anything about where it is other than it's in this interval somewhere. We need to rely on other means to actually discover which value of c will work. But look, I know what the derivative of f is. Remember, we calculated it up here. So I'm looking for where this expression right here, 3x squared minus 6x plus 2, equals this expression. And for that matter, I know what f of 2 is and f of 0 is, or at least I can compute them. There's my formula for f of x right there. Let's do that first. Again, just plugging 2 into the formula for f. Looks like we're going to have to cube it and square it, multiply by a 3 and a 2 there. There's that expression. And that comes out to be a 2. And same thing for f of 0. We need that as well. And that also comes out to be a 2. So plugging these two things back in here for f of 2 and f of 0, we have the derivative at c is 2 minus 2 over 2 minus 0, or 0. Let's push things up a little bit more, so we got some more room. But as we said before, we know what f prime is. It's this expression right here. So if I want to find f prime of c, the derivative at c, I just need to plug a c into this expression here. Well, that gives us this quadratic in terms of c sitting here. Of course, if I'm interested in the value of c that makes this work, I'm just looking to solve this quadratic equation. And we can approach that in the normal way. We could try to factor it. It doesn't factor neatly, and so we punt a little bit and use the quadratic formula. And a few quick calculations later, it looks like c must be either 3 plus or 3 minus root 3 over 3. Now, it's important to realize what we actually have our hands on here. These are the values of x where my original function has tangent lines with slope equal to that special secant line we talked about. However, these x values might be anywhere. Depending on what function was involved here initially, lots of different things could have happened. And lots of different solutions might be found, but the only ones I care about are the ones guaranteed by the mean value theorem. Here again, let's remind ourselves of what that says. There exists at least one value of c where all this is true, where c is in the open interval from a to b. I need to make sure, if I'm going to report this as a point guaranteed to exist by the mean value theorem, that the x values I'm looking at are actually between a and b, or for us, between 0 and 2. Let's push this all the way out. Okay. Now, as luck would have it, both of these actually do lie between 0 and 2. Keep in mind, square root of 3 is 1 point something. So if we do an addition there, we've got 3 plus 1 point something, not quite 3 plus 2. Even 3 plus 2 would be 5 over 3, which is less than 2. And 3 minus root 3, that'd be 3 minus 1 point something, no smaller than 3 minus 2 over 3, which would be a third, which is still positive. Okay, so we need to double check those values. If we found one of these values was not between 0 and 2, not in our interval, then its existence is not guaranteed by the mean value theorem. And again, just to be clear, even though we did in this case find two values of c that make this work, the mean value theorem only guarantees that we have at least one such value of c. Okay, but let's go ahead and proceed with both values here. Recall, the original question asked about points on the graph, so we need ordered pairs to go with these x values that we have just found. Okay, so that requires a little bit more work. If these are the x values, if these are the inputs, how do we find the y values? Well, we have to plug them in. Plug them into what? The original equation for f, which is, if you recall, x cubed minus 3x squared plus 2x. So I'm going to evaluate this function at these 2 points. Okay, so in the interest of efficiency, although it does come at the cost of a slight abuse of the notation, let's go ahead and do both of them at once. So what is f of these two x values? Well, plugging into our original expression for f of x, we've got this, which is a bit of a bear to expand, but we can do it. Multiplying everything out in the numerators, we get this. Notice we need to get some common denominators before we can put these together, so that's our next step. And let's push things up a little bit so I've got some room. Here we have the same expressions with the common denominators. And do notice the way I've written this. This is plus or minus. This is minus or plus, which means when this is positive, this must be negative, and when this is negative, this must be positive. Now, the amazing thing here is, when the dust clears and you collect like terms, all you have left is that. So those are the y-coordinates to match our x-coordinates, and as such, the points where we have tangent lines whose slopes agree with the slope of the secant line we talked about earlier, those points are these guys right here. Okay, we're done. Hope that helps.